Okay, thank you, Carl, for the introduction, and thanks for the invitation. So good morning, everyone. My name is Emmerick Vandervelpen. I am a CFD application engineer at Infinite Simulation System, and we are an Ansys Elite channel partner based both in the Netherlands as in Belgium. Today I want to talk with you about this exciting topic, GPU accelerated CFD simulations at the Ansys Fluent solver. And together with that, how to use that on an Hortense supercomputer. Later on in this session, Peter will join, Peter from the Innoptus Solar Team, and he will talk about how they used the Ansys tools to compete in the Australian World Solar Challenge. After that, I will return to you with some additional benchmark results from the Solar Team case. But let us get started. First of all, the roadmap of my presentation. First, I will give you a very short introduction about Fluent. Maybe some of you are less familiar with it. Then afterwards, I will walk through the GPU story, the rise of GPU, the introduction of GPU into CFD, some extra accelerations inside the complete CFD workflow, and then we will put it to the test. We will take Ansys Fluent GPU to the supercomputer with our Drive R case study. But first, what is Ansys Fluent? Ansys Fluent is a widely used, the most widely used commercial CFD software. It's already there for more than 40 years, and it's an expert in the domain of fluid dynamics. It's a single platform both for fluid flow, heat transfer, chemical reactions, and is applied across multiple industries. It has versatile physics. It can handle any type of flow, from a laminar pipe flow until an unsteady LES simulations. It can be used in combustion together with radiation. We have a wide spectrum of turbulence modelings, from RANs up to stress blended eddy simulations to LES simulations to achieve the highest fidelity scale resolving simulations. On top of that, they're working hard to get a good optimized meshing workflow. Some years ago, we introduced the polyhex core method inside the Fluent Mesher. And 2 years ago, we introduced the rapid octree meshing workflow, which enables it to scale up to billions of cells on an HPC cluster in just half an hour. On top of that, we can combine the Ansys Fluent simulation tool to automate your complete workflow or integrate with other tools like Ansys Mechanical, CFX electronics tools. This can be done through Workbench or OptiSlang, or you can customize it yourself through the PyFluent, which is an API which makes it possible to Pythonize your Fluent workflow. On top of that, Ansys works hard to always improve in terms of HPC, high performance computing. Year by year, they try to upscale the simulations to be able to run on supercomputers like the Tier 1 system. But then the topic of today, GPU computing and how it's also affecting CFD calculations. But first, we have a short look at the CPU performances year by year. I've shown here the well-known graph of Carl Rupp about the evolution of microprocessors, the trends in the past 50 years. Some key takeaways here: we saw an exponential increase in transistor, up to 6 times more cores per core, transistors per core. But we saw that the single core performances increased relatively slowly. So the most improvements were just made by introducing more cores on one processor. On top of that, we see that the frequencies, the clock speed of these processors is flattened, mainly due to thermal limitations. And that's also what we see in the power usage, which is quite flattened out. That's also, if you then look at our CFD performance on these CPU processors, then we see that over the years we made drastically increased performances, but this was mainly due to the fact of increased cores per processor. If we look from 2080 until 2023, we see that we go from 8 cores to 112 cores on one processor. It's an increase of 14 times. So most of the speed up, the 91% time speed up, is achieved by these increased core counts. It's just 6.5 times due to the performance increase per core. So we're seeing there the ease of accelerating with CPU is quite of limited or flattened out the last years. We look forward to a new pathway where massive parallelism can be achieved, and that's the use of GPUs. So why these GPUs are much better for CFD performances? That's mainly due to the that CFD is a highly memory bandwidth limiting problem. CFD is an iterative solver. Every iteration, the solver moves large amount of data between your memory, your RAM, and the processor. So actually, your bottleneck is not really the compute power of your processor, but more the data throughput to your memory and back. So adding more cores beyond the memory bandwidth is actually limiting your efficiency. For example, if you look at the AMD EPYC used on the Hortense, he has 8 channels per socket, but actually to achieve optimal performance, we can just use 25 to 50% of the total cores of that CPU. If you then introduced a GPU in this topic, then we see that we can drastically increase these performances. But why is that? That's really due to the drastically increase of memory bandwidth compared to the CPU. So if we look at the chart over here, in the top we see the AMD EPYC, which is the processor used on the Hortense supercomputer. Then we see the NVIDIA's A100 and H100s, and these drastically increase the memory bandwidth. If you look at the A100 with 80 gigabytes, which we will use, it's 10 times more memory bandwidth compared to a CPU. So in terms of CFD, GPU can really win the game and really transfer all the computing resources to GPU due to much more ALUs, so arithmetic logic units. It has a lower energy consumption and a much higher bandwidth memory. How we can explain these big differences and the change to GPU, then we have to look at the architectural differences between a CPU and a GPU. On the left picture, you see the architect of a CPU, which is optimized for serial tasks. We have some powerful cores there, controlled by a control unit and supported by a large cage. This is very good for complex tasks in serial. On the right, we see the GPU architecture built out of thousands of lightweight arithmetic units with a minimal cage, and which is really optimized for this raw throughput. So the key insight in CFD is that the solver performs the same calculation on every cell in the mesh for a lot of iterations, and those calculations are largely independent one to another. And that is really perfect and matches the GPU performances, which is designed to run millions of identical operations in parallel. So if we then look at the key features and key numbers in the bottom, one single GPU can, just based on memory assumptions, can speed up 5 times compared to an AMD Milan node. It can be 7 times cheaper and 4 times less energy consumption. And it has, of course, 10 times more memory bandwidth. Of course, these are the numbers published by Ansys, but later in this presentation, I really want to couple them with the benchmarks I did on the Hortense. Then how GPU enters the domain of Fluent, and how brings the GPU extra accelerations to the Fluent calculations. So some years ago, Ansys completely rewrote the Fluent Fluent solver, which was there for 40 plus years, from the ground up, natively to run on the GPU solver. So the data stays inside the GPU's memory throughout the complete calculation, which really eliminates the data transfer bottleneck between your memory and your compute unit. Important to note, it's not the same as the GPU offloading, which was done some years ago, where some parts of the calculation were offloaded to the GPU, and the rest of the calculation was done on the CPU. If you look at some key advantages of this GPU solver, you use the same case file because it's built on the same architecture, the same principles. You can just insert your case file of your CPU solver inside the GPU solver. The solver is hardware agnostic, so you don't need to use only NVIDIA. It's also possible to work on the AMD or ROCm technology. And for the GPU, we see that in most cases it's more robust in single precision than the CPU equivalent benchmark tests. This is mainly due to the fact that the GPU solver was completely rewritten from scratch, with single precision as one of their key targets, thanks to its modern architecture. So completely rewritten the numerics. It can really perform very well on single precision FP32 cores without compromising numerical stability. So how we can use the Fluent GPU? We have two ways. We can use Fluent through batch mode, so without the GUI opened. Then we can just add a dash GPU component to your batch command, and then the Fluent GPU solver opens. In this way, the T4 means you will use 4 GPUs. The other way is through the GUI, through the launcher. When you open Fluent, it automatically opens this window. You can then check the native GPU, and then instead of opening in CPU mode, it will open in GPU mode. You will also see the GPUs available on your machine and the number of SMs or streaming multiprocessors available on that GPU. Some common guidelines is if you have one GPU, you run the calculation on one CPU. But for import and export, we sometimes use more CPUs. In terms of Ansys licensing, this usage of the GPU solver requires a CFD enterprise license, and inside these and license 40 SMs, streaming multiprocessors or compute units are included. If you want to go to the bigger GPUs, you need additional HPC packs. But what exactly is an SM or streaming multiprocessor? That brings us to the next slide. So a streaming multiprocessor or SM is the basic compute unit inside an NVIDIA GPU. Each SM contains multiple CUDA cores, up to thousands, which are your ALUs, so your workers. On top of that, also consists some tensor cores, not really used in CFD, more used in AI and machine learning. Some special function units, a warp scheduler, and a large register file. Also in AMD cards, more or less the same architecture is used. We call it compute units with a similar structure with their own stream processors and scheduling logic. So these SMs or CUs are how we try to compare GPUs similar to core count in CPUs. But of course, not always. The more cores or the more SMs you will have, the better your performance is, because like I already told you, memory bandwidth is even more important. That's shown in the table on the right, some different GPUs with some different architectures year by year provided by NVIDIA. Then we see that actually the L40 has more ASMs than even an H100. But if we then look at the memory bandwidth, there is a key difference over there. So in general, the L40 be slower than the H100, even though higher ASMs. So that's a key takeaway for this slide. So if you're looking to purchase a GPU, it's always very good to look at the memory bandwidth and not just only the ASMs. But it's important to remind that ASMs is the way at Ansys we quantify the HPC performances. Then a general table of some data center GPUs. I have highlighted the A100. That's the one I used. You see the memory bandwidth for them and also the equivalence. But you also see the maximum number of mesh shells that can be run on that case. So of course, the GPU is a very promising story, but like I said, everything is done inside the GPU. So we also have to look at the memory of the GPUs. Also, that is increasing, but sometimes if you go to big meshes, that's something to take into concern. Some general memory usage guidelines. So for single precision, it's 1 to 1.5 gigabytes per million cells. If you go to double and a coupled solver, then we have to increase the number of gigabytes per million cells. So these guidelines can be used for your case to get an estimate how much cells you can run on your GPU. Some practical tips when using the GPU solver. Like I said, in most cases, it's numerically stable and accurate in single precision. So always first try single precision and then afterwards go to double precision if needed. Try to fill the memory for best efficiency. So of course, the same with CPU. If you go to very small cases, then it's not efficient to go to very high GPUs or a lot of GPUs. If we have bigger meshes, which doesn't fit inside one GPU, then we can go to multiple GPUs and spread the CFD calculations over these GPUs. So the Fluent GPU solver is introduced in 2023 and is increasingly popular year by year. But like I said, they completely rebuilt the GPU solver from CPU to GPU. So this means that all the physical models and numerical models needs to be transferred. So that's done by phase matter. So therefore, each year, new release, new features are added. So that's a common question, which physics are now supported on the GPU solver. And since it's already the fourth year, fourth release or fifth release, a lot of features are already transferred. For external aerodynamics, we can run the full range from RANS models, transition models, including curvature correction, and also both compressible and incompressible flows can be solved. Even on the scale resolving simulations, we have a lot of possibilities. We can run a large eddy simulation, stress banded eddy simulation, include wall modeling or resolved LES, and year by year the numerics are increased. Important to mention is the increasing CFD speeds achieved with these GPU enables customers to start looking at scale resolving simulations, while in the past this was only possible in small cases for academics. In terms of heat transfer, conjugate heat transfer, so solid and fluid regions together can be solved. Both natural and forced convection due to compressible flow, and surface-to-surface radiation and discrete ordinate radiation can be solved. In terms of combustion and multiphase, the eddy dissipation model and flamelet generated model are available both in adiabatic as non-adiabatic flame. This 2026 R1, which was released beginning of March, the thickened flame model was added together with the chemistry algorithmization. In terms of multi-phase, so when we solve more than one phase, for example, water and air, we talk about multi-phase. We introduced the volume of fluids model, this release, together with the energy equation. Species transport can be solved, both for the surface tension as phase change we can now solve. And of course, also compressible liquid. On top of that, porous media and sliding were features that really were asked for. Also interesting to mention is that Python UDFs can be used to customize your Fluent setup more. And this year release, we focused on battery models, the thermal abuse and a reduced order model were integrated. Then, of course, it's a very strong message, the GPU solver, and very interesting. But of course, we still need to prove his trustworthiness because we completely rewritten the solver from scratch. And therefore, Ansys released year by year a white paper with several cases on the GPU solver, where we typically see that the results CPU versus GPU are below 1%. And in most cases also match very well with measurement data. In the top left, we see an automotive case, a side mirror solved with an SBS simulation, where we see that the pressure distribution coefficient matches very accurately at more than 80 probe locations inside the domain. And also the vortex structures were fully resolved. Then we looked at a landing gear simulation where we were interested in the drags of the front and rear wheels, but also the acoustic sound waves generated due to this landing gear. These results matches very well both CPU compared to GPU, but also compared to wind. The bottom left, we see a marine propeller where we looked at the thrust, torque, and efficiency, which exactly matches the test data performed on the propeller. This case used the moving reference frame on top of the turbulence model and a coupled solver. The last one was the Onera wing, where we measured the pressure distribution across multiple points. We saw very good matches between GPU, CPU, and our measurement data. The message is quite straightforward. You don't give up accuracy when switching to the CPU solver. You can just achieve huge speedups, but these validations can also be seen in our own cases. So of course, if we speed up the CFD calculation itself, we also have to look at the mesh. Therefore, Ansys also worked very hard on rapid octree meshing approach, which enables you to massively run parallel meshing generations up to millions of cells. It's a top-down approach from CAD to volume mesh in an automated way, where you will work with a completely structured projected octree mesh. This meshing method allows you to go to billions of cells on an HPC cluster in just 25 minutes. We see a customer case on Volvo, the AX90 electric vehicle, where they could reduce their simulation time from 24 hours to 6.4 hours. Same equivalent hardware in terms of cost. They used the NVIDIA Blackwell GPUs, and compared to their previous cluster of 2000 cores, they achieved a speed up of 2.5 times. On the top right, we see different automotive benchmarks, but the main conclusion for all of these cases is that by means of the GPU and the octree mesh, we can now have multiple options in my engineering workflow. We can look into more designs in the same time frame, or we can reduce physical prototyping and wind tunnel testing, because we can now look at more options for one car to really get a broad map of my car. Or we can look into higher fidelity meshes and physical models like an LES or an SBES simulation, which we can now introduce inside my design cycle due to these increased speedups. Or we can just focus on shortening our design cycle and improve our go-to-market, speed up our go-to-market. On the other hand, we can keep the same time periods, but just reduce the costs with 7 times and energy consumption with 4 times. But of course, these are all the cases performed by Ansys in the past. Good to also bring it to own tests on the VSC. Therefore, we work together with the VSC to deploy this Fluent GPU solver on their hardware. So the VSC, Flemish Supercomputer Center, provide HPC infrastructure for researchers and in Flanders. They have more than 100,000 of cores, 160 GPUs, the A140 and 80 gigabytes, and they have an impressive 5.4 petabyte of storage. Over here you see the different partitions available at the VSC. I mainly use the CPU partition, the Milan, which is the most recent of the two, which gives you 128 cores per node, and the GPU partition, Rome A100 with 80 gigabytes. On top of that, I also use the web portal access and of course the SSH clients have access to my data and submit the jobs. This is how my workflow looks like. First of all, I connected to the on-demand or web portal to upload my case file. From there on, I could perform the solve, etc. Then I connected SSH client with my private key. I made use of a login node, and from that login node, I could write and submit my PBS script. So that's my scheduler script. I performed the model swap, so I have to select my partition. So either the CPU partition or the GPU partition. And then I had to submit the job with the QSub of my PBS script. And then I could monitor it in the SSH client, both if it's submitted, but also I could monitor my output file. And then I could extract my results through the web portal again. My preference was to use the web portal because it's very easy to use and gives you a very good overview of my different data sets. Then my benchmark setup, I used Ansys Fluent 2025 R2, which was released last year to test all the cases. So I used either a CPU partition or a GPU partition. CPU I tested from 96 to 4,000 cores on 1 to 32 nodes. GPU, each partition had 4 NVIDIA A100s on 1 node, and I tested 1 to 32 GPUs, so 1 to 8 nodes. My testing protocol looks like I first ran simulation until convergence, which was from 800 to 5,000 iterations. And then afterwards, I saved that case and data file, run my benchmark cases, which were 20 iterations per configuration, which gives me a consistent methodology across all my configurations. I have put an example of my GPU batch command with the components step-by-step explained. So I launched Fluent 3D double precision with 4 GPUs. And then I enabled, of course, the GPU solver, but I also included the GPU remapping because in reality, case and data file import is still done on CPU. So like I already told you, per you use 1 core. So in this case, otherwise I would just import the case on 4 cores. Therefore, I enable GPU remapping, which enables you to first load the case file on all my available CPU cores. So in this case, 48 for fast parallel input and output. And then afterwards automatically switch the GPUs, which is 4. I used InfiniBand interconnection and Intel MPI. And I used an HPC Ultimate license, which actually includes both the full enterprise solver capabilities, which needed for Fluent, but also unlimited CPU and GPU scaling with just one single license increment, which makes it very easy. You don't need to bother about, do I have enough licenses or not? We can go from 4 to 1,000, of course, with just one license. Of course, I also had to run my journal file, which I'll always use if you use Fluent through batch to go step by step to my Fluent setup. I had to install Fluent 2025 R2 locally. This was done by the VSC. For the CPU benchmarks, I reserved a full node to achieve optimal performances. And for the GPU, I added an extra component called scheduler_ppn to highlight to Fluent how much GPUs per node there were. Otherwise, it could be that if you have more than 4 GPUs, for example 8, that they were all assigned to one single node. Okay, so I explained my workflow at the VSC. And this workflow I used to perform my benchmark case. I have done one myself from an Ansys benchmark case, which is publicly available to all customers to test. It's the driver 50 million cell case, which uses the octree meshing technology. I ran double precision just to get a more honest comparison between CPU and GPU for the same accuracy. Probably more speedups can be go to single precision. I used the segregated or simple solver type. It's a steady state case with the Gecko model, which is a turbulence model built to fine tune your turbulence parameters for your case. This case needs 5,000 iterations to convert, and I ran my benchmark tests on 20 iterations per setup. Before looking at the performances numbers, let's first confirm that the GPU solver produces the same answers as a CPU solver. In the left, we can compare qualitatively, so both velocity field, the turbulent wake structures, pressure distribution looks more or less indistinguishable between GPU and CPU. But on the right, we also see the quantitative validation, where we looked at the pressure distribution coefficient across we saw that they're matching very well. And this confirms that there is no accuracy trade-off between CPU and GPU. Now the performance results. So I performed several benchmarks on CPU and GPU. This chart shows you the time per iteration. So it's the total time of my test divided by 20. On the left, we see navy the bars for the CPU, on the right for the GPU. Performance-wise, we see that up to 2,000 cores, we see speedups achieved. Then we get negative scaling because the problem becomes too small to run on so many cores. On the GPU side, we see that even one A100 already performs better and almost similar to 1,000 cores or 500 cores. If we then look at the sweet spot, it's 8 or 60 which will run in 0.07 seconds, which is significantly faster than the best CPU performance. The key numbers, if you look at the best CPU case, which is the 2000 core case, and the best GPU case, we still achieve a speed up of 5. In other words, if we just use one GPU node of 4 GPUs, it's equivalent or even outperforming 24 nodes on a CPU cluster. Then if you look at the linear, both on GPU and CPU side, on the left, we compare the GPUs with the CPU nodes. Then we see that the CPU curve in navy tracks ideal line more or less until 1000 cores. And at the GPU, it's more or less plateauing at or 8 GPUs. On the right, I shifted the graph a little bit and I looked at the compute units. So I compared SMs with CPU cores, which is how at Ansys we try to compare the results. If we then look at relative speedups, if we compare with CPU nodes, we can achieve speedups of 8 to 6 times at the left. If we shift the graph a little bit and we just look at compute nodes, so SMs to CPU cores, we can achieve speedups of 9 or 7 times. Of course, if we go to the higher, we see that the GPUs are off, the same with the CPU. The speedups are relatively smaller, but still we see speedups of 5 times. I've put the Ansys HPC packs on top, so that's how we quantify the HPC licenses to give you some general parsing, how much speed up we can get for the same licenses. Let's translate this to some numbers in cost and power. I use the VSC for business pricing, so that's the commercial prices for a core hour or a GPU hour. If I then look at the GPU performances, the cheapest is just using one GPU. That's only 70 cents. And if I compare that one with the cheapest CPU option, it's almost €5. So it's 7 times lower cost to run it on a GPU. But also in terms of energy consumption, the 4 GPU is the most efficient one with only 0.4 kilowatt hour. Compare that one with the CPU, we can consume 6.5 times less energy, so a lower carbon footprint. What makes these numbers really compelling? The cheapest option, a single GPU, is also the easiest one to deploy, either on a cluster, but also locally on a workstation. It's just one GPU and it's 5 times cheaper, less energy consumption. And as you can see over here, it's also much faster. For a lower cost, you still can achieve speedups. So in terms of cost, 7 times cheaper. In terms of energy, 6.5 times less energy consumed. Then perhaps a more impactful slide for really looking on engineering manager perspective, how we can now tackle this one. If I just take a budget of €100 to make it easy, on the CPU, I could run around 20 calculations with that budget. If I then go to a GPU equivalent, I can run 100 simulations for the same budget. Also in terms of wall clock time, if I look at a general CPU setup, it's 2.5 hours, which is a quarter of your working day. If I then go to a GPU, I could easily reduce an hour, so just during lunch, or even further reduce it to 6 minutes. So just taking a coffee and you come back and your results are ready. So to close my first presentation, some key takeaways taken my tests on the VSC. First of all, for any type of setup, the best CPU versus GPU performance, we can achieve a speed up to 5 times, where we can just match one node with 24 CPU nodes. We validated the accuracy of my simulation, both CPU for GPU. It can be 7 times cheaper and almost 7 times greener or lower carbon footprint. We can conclude that the VSC Hortense is GPU ready with 160 A100s, either 40 or 80 gigabytes, and more to come. And in budget, we can now buy a lot more CFD simulations, 144 compared to 20 on a CPU, which enables you to run more designs, more situations, or just go into more accurate simulations, like we can see over here with the driver 500 million case, which is an LES simulation run on 4 H100s.